Let's talk about magnetic induction. Suppose we have a magnetic field going into the board, and we have a positive charge moving to the right. Applying the right-hand rule will tell us that the force will be acting up on that positive charge. That's the magnetic force produced when a charged particle moves through a magnetic field. And previously, we've established that this will cause the charged particle to curve, changing the direction of the velocity vector, and therefore changing the direction of the magnetic force. But what if this charged particle was inside a wire, and that wire was moving to the right? The charged particle will still get a force acting up, but it won't be free to move in a circle. It's going to stay inside that wire. The charged particles tend to accumulate at the top, and that makes the top of the wire positive. They're moving away from the bottom, which makes the bottom of the wire negative. Now imagine that this wire was riding on conducting rails, so that there was a circuit made through an ammeter and a resistor. The positive charges could flow right around. Well, what we say now is that we have induced a current by moving the wire through a magnetic field. This is what is meant by magnetic induction. Let's see if we can demonstrate that by passing the wire over a strong neodymium magnet, hooking it up to the galvanometer, which measures small amounts of voltage or current. Sure doesn't look like it's doing much. Barely moving that needle. So what's better than moving one wire past the magnet? How about moving 100? Oh, now we can see that needle move. What's really interesting is that it doesn't matter that the wire moves past the magnet or the magnet moves past the wire. It's relative motion. That's all that matters. Now notice that with the magnet really close to the coil, we have nothing flowing. It doesn't matter that you have a strong magnetic field. You have to have a change to occur to cause induction. Either the wire has to move past the magnet or the magnet has to move past the wire. If there's no motion, you do not get any induced current. Also notice that when the magnet moves one way, the current is induced in a certain direction. And when the magnet moves the other way, the current is induced in the opposite direction. That all can be explained using the right-hand rule. Now we can see that as the wire moves to the right, the current wants to go in this direction. But what if the wire is moving the other way? Your hand is going to now go in this direction and will push down on that positive charge. That causes the wire to become positive on the bottom, negative on the top, and the current will now flow in the other direction. Okay, but how does that work with a loop of wire with a magnet approaching the loop? Well, if I draw it like this, the field lines that come out of the magnet are going to be moving past the wire. It's a lot harder to draw field lines that are moving past the wire than to draw the wire moving past the field lines. It doesn't matter what I do as long as the relative motion is the same. So I'm going to make the wire move past the field lines. We know that the field lines leave the north pole of the magnet and loop around into the south pole. I'm going to leave those field lines stationary and now move the wire. I'm going to look at 2 points along the loop. At the bottom, I can put my thumb in the direction of positive motion, my fingers go in the direction of the field lines, and there will be a force on a positive charge in that wire coming out of the board. Up at the top, I can put my thumb in the direction of positive motion, my fingers in the direction of the magnetic field, and there'll be a force into the board. That makes the charged particles loop around, go behind, and then come back out and around. Well, we can just zoom in on each one of these to get a better look. This circle represents a cross section of the wire right at this point. So I'm zooming in on this little part of the wire and drawing it as if we sliced right through it. I'm looking at just a section of the magnetic field that is going down. Now, it's not exactly perfect. in real life, it's going to have an angle to it. But at some point, the field line will curve around, and I'm picking the most perfect point. Now imagine this part of the wire is moving towards the magnet. That's a positive charge in the wire. I put my thumb in the direction of positive motion. My fingers go in the B field, and the charge gets forced out. So I'm putting a dot in the cross section of the wire to represent the current coming out of the board. I'll do the same now at the top, a cross section of the wire from that point right here. And we can see with my thumb in the direction of positive motion, fingers in the direction of the B field, the force comes out of the palm of my hand, and that makes the current go into the board. Back to the loop, we can now see that the current is going to go like this, come around, out, and follow a curve out in front, back and behind. So as viewed from the magnet, we would say that the current is going counterclockwise around that loop. Well, what would happen if the magnet started moving this way? It would be the same thing as taking the wire and move it that way. To keep things simple, I've only drawn the cross section of the wire at the top and the bottom, and we can see that it's moving to the right. That's the same thing as moving the magnet to the left. The magnetic field curves around, and I've drawn it specifically just where it would go through these cross sections, up or down vertically. That makes the diagram easy to understand. Right hand rule at the bottom, thumb, fingers, force goes into the board. I'm going to have an X here. At the top, thumb and fingers, force comes out of the board. I'm going to have a dot. Hey, now the current is going to loop around and go in the opposite direction. As viewed from here, we would say that that current is going clockwise. We've induced a clockwise current. Let's go back to our original diagram. Again, the positive particle is in the wire. It's moving to the right, and the magnetic field is going into the board. So we have a magnetic force going up. Hey, we can apply a formula to this. The velocity is perpendicular to the magnetic field. So we don't have to worry about any taking components. We can just say F magnetic is equal to QVB. If this force acts on that charge through a distance, and that distance is L, and this force is parallel to that distance, can you think what's going to happen? Hey, we're going to have some work done to this charge. Force times distance is work, and the force is parallel to that distance. Putting these two formulas together, we can say that the work is equal to QVB, that's the force, times the distance. I'm going to divide both sides by Q and have work per charge, which will be equal to VBL. Does anybody remember what work per charge is? Yeah, it's a voltage. And I write the V like this to distinguish it from the velocity over here. This is the voltage generated by this wire moving through the magnetic field. If it's got this length, then it's moving at that velocity, and we have the magnetic field strength. So it's VBL equals the voltage. We often see this written as EMF equals VBL. This stands for electromotive force. It's kind of an old term, but we still use it. It's stuck around. It is not a force. Electromotive force is a voltage. Yeah, go figure. Like, this stuff isn't hard enough. Well, now we have a problem. Just to see if we understood any of that stuff we're talking about. Find the induced current. Well, that's the induced current due to the motion of this wire through the magnetic field. The velocity is in this direction. The current will be this way. The positive charges moving along this wire are going to gain energy due to the work done to them as we move through the magnetic field. As the current passes through the ammeter, it's then going to go through the resistor, and that's where the charges will lose their energy when they come back to here. So how much voltage could we say is across this resistor. It's going to be the voltage lost is equal to the voltage gained as we go around this loop. We're going to say it's equal to VBL. We have 10 meters per second, 5 Tesla, times 0.4 meters. And I get 20 volts. Applying Ohm's law, V equals IR. We get a current of 1 amp. Now I have to ask you, you saw me move this wire in the video. Do you think that wire is just going to keep on moving by itself once I set it in motion? Do you think that there's something going on here with the energy? Where does the energy come from? Obviously, this thing is generating waste heat here. It's got to come from someplace. Well, let's take a look at the force acting on this charged particle. We said that it was going to be this way, and that the current is going to start to move up. But once that current starts to move up, we can say that we have another velocity going up. We have the velocity going this way initially, but then we have another velocity going up once this current starts going. There's charges all along this wire. I'm going to talk about this charge up here so as not to confuse it with the diagram down here. We have this positive particle moving up. I put my thumb in the direction of positive motion, my fingers in the direction of the B field, and there will be a magnetic force coming back this way on that charged particle. We can think of this as the first magnetic force acting on the charged particle. Once the charged particles move, then we can call this the second force acting on that charged particle. It's a second application of the same right-hand rule. But notice what the direction is of that force. It's backwards. The wire is moving this way, but that force is this way. So that's going to cause this wire to slow down. How do we maintain this velocity? We are going to need to push on this wire with the same force as this is holding us back. So to determine this force, we're going to need to know this force. And there's actually a whole bunch of those forces acting on all of these charges, pushing it backwards. Well, we know that the magnetic force is equal to QVB. But that V is the velocity of these charges moving up through the wire. We don't know what that velocity is. But I do know that that velocity is equal to the length of this wire divided by the time it takes the charges to move up. If I move this time underneath the Q, I can now say Q per T, that's current. So we have ILB is equal to the magnetic force acting on the whole wire. This entire wire has this much force holding it back. That's how hard we have to push forward to maintain constant velocity. Now I can calculate how hard I have to push. 1 amp times 0.4 meters times 5 Tesla. I have to push with 2 newtons. Time to update the problem. Let's find my power. Power equals force times velocity. I'm putting out 20 watts of power. Now we're going to find the power consumed by that resistor. Electrical power is I squared R. 1 amp squared, 20 ohms, we have 20 watts. Way too many 20s in this problem. Sorry about that. But the fact is, the power that I put into this is equal to the power consumed by the resistor. This electrical energy isn't coming from nothing. It's coming from me doing work. This is a generator, an electric generator. My mechanical energy is being converted into electrical energy. And that's what we see here. This generator takes the wire, moves it past the magnets. I'm generating a voltage, and it's lighting up the light bulb. If I let go of the handle, it stops. I can't just push it and have it keep going. I can actually feel the resistance of me having to push the charges through the wire. The magnetic field is not doing the work. I'm doing the work. Now, if I disconnect this, it's real easy to push. And in fact, it carries through a little bit. There's some resistance in here. But if I had no friction, then this thing could just keep on going. I'm not doing work unless there's current flowing through the circuit.